We have a great gift that has been denied to the other living creatures on this planet. We have imagination, which we are capable of giving shape to in the space around us. The most noticeable element which we encounter every day is architecture, a wonderful image of human creativity. And which works of architecture should we see during our lifetime? Top 10. The art of architecture reveals the answer to this question.
Top 10. The art of architecture.
In this episode, you will see 10 most amazing bridges listed from oldest to newest. They are the type of engineering architecture which not only makes our lives easier, but also more beautiful. Each of the 10 bridges we will show to you is a technical miracle, an exquisite piece of art that has left an ineffaceable trace in the history of human construction culture. However, for all of them it can be said that walking or driving over them or passing under them on a boat is an unforgettable experience.
The most amazing bridges. Number 10. Brooklyn Bridge, New York City, United States.
It is undoubtedly one of the iconic structures of New York. It connects the boroughs of Manhattan and Brooklyn by spanning the East River. The genesis of neo-Gothic Brooklyn Bridge is not only a story of the indomitable energy of the members of one family, but also a story about the American dream, an unwavering faith in modern technology, which in the 19th century knew no bounds. The father of this bold idea and project of a bridge was an American architect and engineer of German descent, John Augustus Roebling. Roebling began to work on the bridge project in 1867. After his untimely death, Roebling's son Washington became in charge of the construction.
The Brooklyn Bridge had one biggest difficulty, it was foundations. The engineers tried to find the best place where to put the pylons. It was first thing. And the second was how to build the pylons, because the riverbed is muddy and very deep.
Washington decided to use caissons, large vessels with bottoms up that enable work underwater thanks to air buoyancy, for building the massive foundation of the Brooklyn Bridge. Its construction was commenced on January the 3rd, 1870, on Brooklyn banks of the East River. A caisson, sized 50 by 40 meters, was transported to the designated place and then lowered into water. After its steel blades dug deep into the riverbed, the construction works carried out by two groups of workers were commenced. The first group worked above water directly atop the caisson, building the foundation of the bridge tower from huge granite blocks. The second group worked inside the caisson, where they were digging into the earth until they reached solid bedrock.
And this was the most difficult part of this bridge. The caissons were used before, but never in this extent. They were huge, and people were working in the caissons inside, digging the mud under the high pressure that equalizes the water pressure.
The work in the air compression chamber was very difficult and incredibly dangerous. The workers were endangered not just by the stifling air, but also by caisson disease. The first victims of this disease appeared when the second Manhattan side tower was built. At this moment, Washington's wife, Emily, entered the stage. And it was thanks to her that the bridge project saw its completion. The situation she unwittingly found herself in was caused by decompression sickness, which affected Washington's health. Fearing that he would succumb to the disease, Washington initiated Emily into the project. He explained mathematics and construction mechanics to her so that she could replace him in the event of his death. The supervision was taken over by Emily, who has thus left her mark in the history of construction culture.
It remains the oldest suspension bridge in the USA and continues to be a historical landmark. It's an integral part of the New York skyline.
After finishing both the bridge towers, which thanks to their 88-metre height became the tallest structures in the Western Hemisphere, 4 suspension cables anchored in the foundation of both towers were sprung. After they were fitted, specialised cable workers started to attach hundreds of cables on which lies the 3-part frame construction supporting the 26-metre wide deck. Brooklyn Bridge, remarkable technical masterpiece, was inaugurated on May the 24th, 1883. With a length of 1,825 metres and a span of nearly 500 metres, it became the largest suspension bridge ever built by man. It cost an astronomical $15.5 million and 27 human lives. Over the past several decades, the National Historic Landmark has been carefully rebuilt to meet the traffic demands of the late 20th century. Today, it has a 6-lane road and a path for pedestrians and cyclists, and it's lost nothing of its charm.
Number 9. Dom Luís I Bridge, Porto, Portugal.
In the second largest Portuguese city of Porto, known for its sweet dessert wines of the same name, you will find one of the most beautiful bridges in the world. It is located in the historic centre where it spans high above the valley of the River Douro. It acquired its name in honour of Ludwig I, King of Portugal, and it was built from 1881 to 1886, according to the project of a German designer and engineer, Theophile Sierry, a disciple and colleague of the world-renowned engineering genius of the 19th century, Gustav Eiffel.
This bridge hit a record for the biggest trussed arch bridge at the time it opened. It's an elegant structure, and its filigree-like construction gives it a special lightness.
From the construction point of view, the Dom Luís I Bridge is a truss arch construction made from 1,000 industrially produced steel profiles. The truss construction is a reliable construction system where instead of homogeneous vertical walls, the supporting function is taken over by a system of diagonal or rectangular bars that create so-called trusses.
From a bigger perspective, the construction of such a bridge may look like the assembly toy for kids. You bring the profiles, you assemble them, and when the 2 parts of the bridge meet together in the middle, the bridge is done.
The resulting structure, formed by sets of triangles, provides the construction, although it is a lightweight construction well equipped to withstand wind gusts. with the necessary strength, and at the same time, it gives it its characteristic appearance, which became the foundation of engineering architecture aesthetics in the 19th century. Unlike civil architecture, this architecture did not hide the support structure under layers of richly decorated facades, but left them naked, proudly exposing them to be admired. It was engineering architecture and its bold structures that in the early 1920s inspired Le Corbusier to write his manifesto, Toward an Architecture, which contained the famous advice, "Let us listen to the counsels of American engineers, but let us beware of American architects." The foundation of the bridge consists of a massive steel arch spanning 172 meters, which in the height of 45 meters bears the upper deck. Originally, it was intended for pedestrian traffic and railway transport, which passed through its middle part. For this reason, the deck is supported by 6 supporting truss girders. 4 of them rise from stone pylons, while the other 2 are anchored to the bridge arch.
The bridge was built in the 19th century, and the 19th century is steel construction age. So it's kind of typical construction for that age. And Gustav Eiffel built many structures around Europe of this kind.
The Dom Louis I Bridge was inaugurated on October the 31st, 1886, and a year later, the lower deck intended for normal ground transportation was opened as well. It is supported by 4 subtle beams suspended to the bridge arch, to which at this level enters through triumphal arches whose slant shapes are reminiscent of ancient Egyptian pylons. Porto is no longer crossed by once popular trade routes, for which the deep valley of the river Douro posed an unpleasant obstacle, while bridges were a welcome shortcut. But even though the main reason for the construction of Porto bridges no longer applies, their presence in the Portuguese city is now an essential part of Porto architecture. And the most imposing one is undoubtedly the Dom Louis I Bridge.
Number 8. Tower Bridge, London, United Kingdom.
In the heart of historic London, you will find one of the most famous bridges in the world, the Tower Bridge. It has connected the Thames Bank, Southwark on the south bank, and Tower Hamlets and East End on the north bank. In the second half of the 19th century, East End, a place originally located outside the city walls, where ships were built and repaired since the Tudor era, began to gradually transform into a centre of industry and commerce. Due to the increasing needs of building developers, industrialists and immigrants, it was necessary to build a new connection between the 2 sides of this area. In order to discuss and resolve this tricky issue, a special expert committee was established in 1877. Its board announced a tender to which more than 50 proposals were submitted. The winner was the project from a city architect, Sir Horace Jones, who was at the same time one of the judges.
The neo-Gothic style of this bridge and the combination of a suspended bascule bridge makes this piece of simple engineering work unique in the city.
The bridge design as we know it was created by Jones's engineer, John Barry. In case of the Tower Bridge, he had to come up with a special system of bridge structure. Barry proposed a 2-tower bridge, where the 2 halves of the deck can be lifted when a ship goes through. He didn't place the towers on the banks, but to shorten the length of liftable parts of the deck and lower the energy necessary to carry out this action, he built them on pillars set in the middle of the river bed. The pillars hold the whole structure and ensure the stability of the bridge.
The bridge itself looks like from fairy tale, but it unfolds enduring structures like steel, stone structures, anchors, and a bit of concrete as well.
To protect the steel core of the bridge, some parts of the bridge were covered by Cornish granite and Portland limestone. Construction work began in 1887. The bridge deck was lifted by a steam engine, which was later replaced by engines installed in the foundations of the two towers. In order not to disrupt pedestrian traffic, engineer Barry placed two separate covered walkways connecting the two towers. After Horace Jones's death, George Stephenson became the head of the project. He changed the architectural design of the bridge towers, which Jones planned to cover with bricks. Stephenson chose a more decorative style of the then fashionable Victorian neo-Gothic. London Tower Bridge, an incredibly elegant drawbridge, was inaugurated on June the 30th, 1894. The ceremony was attended by the Prince of Wales, the future King Edward VII, with his wife Alexandra of Denmark. Those interested in the history of this beautiful engineering structure can learn more if they visit the interactive exhibition inside the bridge. The Tower Bridge is designed for both road traffic and pedestrians. A high-rise footbridge with a modern transparent floor connecting the towers was formerly used mainly for the time when the deck was lifted. Today, it offers a breathtaking view of the modern metropolis, London.
Number 7. Harbour Bridge, Sydney, Australia.
Sydney, Australia's largest city, is world-renowned for its extraordinary opera house. However, in the vicinity of this architectural icon and symbol of Australia, we can find another fascinating structure, the impressive Harbour Bridge. The history of this bridge, inspired by the New York Hellgate Bridge, began in 1914, when John Bradfield was appointed Chief Engineer of Metropolitan Railway Construction, the company that was in charge of constructing the bridge. Bradfield, the spiritual father of the Harbour Bridge, came up with the idea to cross the bay with a cantilever bridge without piers based on the seabed. Such a structure, however, was then unknown to the Australian legislation, and therefore it was necessary to change the legislation first. The tender was won by the English company Dorman Long and Company Limited from Middlesbrough, which had rich experience in constructing large steel arch bridges. In September 1926, ground levelling was completed and construction of the massive foundations of the bridge towers, to which ramps for future communications were connected, began. At the same time, deep in the ground next to the bridge piers, foundations were built into which steel cables were anchored to secure the unfinished arch from collapsing.
This arch bridge has a pillar at either end. These pillars also have another function, apart from supporting the load from the arch of the bridge.
Its construction was commenced in October 1928, and thanks to the use of the latest construction technologies, it progressed speedily. Material and workers were transported to their destination by two large cranes moving on rails integrated into the top of each part of the arch, and the bridge was assembled during 13 months. Its assembly was of course done on both sides of the bay at the same time. Thanks to flawless calculations and perfectly synchronized workflow, both arms were linked exactly in the middle of August 19, 1930. After the last parts were riveted together and the securing cables removed, cranes started to gradually enlarge the deck in both directions from the middle of the arch. The implementation of the deck lasted until June of the following year. The final steps were the removal of all support structures, the completion of the monumental granite pylons, and a preparation for a load test. It was launched in January 1932, and for 3 weeks, the bridge bore 96 steam locomotives.
The reason to have such a huge piers at the end of the bridge is not just for pleasure or architecture purpose. It has very engineering value. It loads the basement in which the arch is anchored.
The coat hanger is also an extremely important arterial road. Every day it is passed over by 180,000 cars. In addition to the 8-lane road, it is crossed by 2 railway tracks, bicycle path and sidewalks for pedestrians. If you love adrenaline and unforgettable views, you can climb to the top of the arch of the bridge and enjoy the view of the bay and the city. This special kind of tourism will take 3.5 hours. It's a hike that beats even those brave enough to climb on foot to the top of the famous Eiffel Tower. But the special feeling to have the whole city at your fingertips is worth it, don't you think?
Number 6. Golden Gate Bridge, San Francisco, United States.
The iconic Golden Gate Bridge has connected both San Francisco shores, divided by Golden Gate Strait, for almost 80 years, despite the harsh weather conditions it faces here. Although at first glance it might not seem so, there are sudden gusts of wind, temperature fluctuations, and strong sea currents shattering against the shores. However, even these extreme environmental conditions could not discourage Joseph Beyeman Strauss, spiritual and actual creator of the Golden Gate Bridge. His dream was to build a bridge that would exceed the existing ones in all respects. A promise to fulfill this dream appeared in the form of the intention of the city of San Francisco to build such a bridge to cross the Golden Gate Strait, through which ships passed from local harbour to the Pacific Ocean.
The best results are achieved when an excellent architect and designer meets an excellent structural engineer, and everyone involved works together to develop the structure.
Construction of the bridge under Strauss's leadership was launched in 1930 with the cooperation of the engineer Leon Moiseff and Charles Ellis, the architect who lent the bridge its remarkable appearance in Art Deco style. The most difficult part of the construction was building the foundation for the southern pillar. It is located 300 metres away from the shore in more than 30 metres in depth. Strauss therefore had to build a makeshift transport pier, which in turn enabled the construction of a waterproof 9,000 tons heavy fender of the size and shape of a soccer field. Only with its help was it possible to build the massive foundation plate of the South Pylon.
The Golden Gate Bridge is a wonderful piece of architecture, but it has very difficult conditions. For example, the foundations, you have to calculate with strong sea currents. You have to calculate with earthquakes and very unstable the seabed.
After the completion of the foundation concrete plates came the construction of bridge towers, riveted from huge steel segments. For each tower, about 600,000 rivets were used. In order to fit each of them in its place, it was necessary to ensure sufficient access to all drilled holes inside the structure. Inside the towers thus emerged an intricate maze of corridors with 90 routes linked together by 27 ladders. Both pylons were completed in the summer of 1935, and with their 227 meters, immediately became the highest bridge structure in the world. In the autumn of the same year, springing of support cables began. Due to their enormous weight, these cables were spun on site, with the help of mostly automatic spinning machines synchronously moving on both cables. The construction of the monumental bridge, for which, according to Joseph Strauss's instructions, a number of new security measures was introduced, was completed in 1937. Only on May the 27th, the day the bridge was inaugurated, 200,000 enthusiastic onlookers were recorded to take a stroll on the bridge. Surface maintenance throughout the year is provided by 28 painters, whose task to prevent corrosion at critical points became the basis of the myth that the bridge is being continuously top-coated. The truth is that the bridge was completely painted during construction, and after that it was painted anew only twice. Nevertheless, you would not dispute the claim that the Golden Gate is perhaps the most photogenic bridge in the world. The 19th century, or strictly speaking, its second half, was a fantastic age abounding with daring ideas, encouraged by almost unlimited faith in the creative genius which man discovered thanks to the unprecedented advances in science and technology. It was primarily construction mechanics and metallurgy that allowed us to build the works we could only dream about before. But the following 5 bridges belong to today, or the recent past. Their construction is directly associated with the dynamic development experienced by the modern civilization in the last 50 years.
Number 5. Erasmus Bridge, Rotterdam, the Netherlands.
The Netherlands may be a small country, but it undoubtedly ranks among the world powers, at least in terms of architecture. This country has more than 100 years of tradition, shaped by whole generations of excellent Dutch architects. But even today, the Netherlands has its architectural world stars. These certainly include the couple Ben van Berkel and Caroline Bos from UN Studia. It is their signature that can be found under the project of one of today's symbols of the city of Rotterdam. The bridge was named after the most important native, a humanist thinker, Erasmus of Rotterdam.
Erasmus Bridge resembles the industrial character of the city. The city was destroyed after the Second World War and was built from steel and concrete.
The Erasmus Bridge is a functional work of art in the centre of Rotterdam, connecting the north and south parts of the city. This elegant bridge, closely passed by routes of 2 tunnels, Maes Tunnel and Benelux Tunnel, was implemented in the years 1990 and 1996. Its total length is 802 meters, and its asymmetrical pylon shaped like an inverted letter Y rises to a height of nearly 140 meters. The pylon shape, resembling the body of a swan, is not a self-serving artistic creation, but a result of rational considerations verified on a computer model.
For this construction, the CAD-CAM method was used. The construction concept and final plans were all created with the help of digital technology.
Because the pylon is not straight and classically shaped, as is usual for most other bridges, it is instead beveled at 2/3 and therefore much less pressured by physical forces that impact it from support cables. The course of load moments by oblique stay cables is much more even on the console pylon than on pylons of usual shape. Even bending moments are significantly smaller. Originally the pylon was to be made of concrete, but it turned out to be too expensive and difficult to make. So in the end, the architects designed it to be made of steel. The south part of the 6,800-ton heavy steel bridge integrates a 90-metre bascule bridge, which is considered the biggest and heaviest in Europe. The Erasmus Bridge design is the result of a uniform design principle. Construction, urban planning, infrastructure, and public functions were combined into one comprehensive gesture to achieve smoothly functioning relationships between parts with various levels of complexity. CAD-CAM method of computer design and computer manufacture, was used for the whole design and the subsequent prefabrication of parts. This method significantly increases the control of the architect over all levels of the construction design. Architectural design smoothly transforms from the initial sketches to the final construction phase. 5 differently shaped concrete pillars, fender, harbours, details, fittings, connections and service equipment have been designed coherently. The insides of the bridge, which connects the southern part of the city of Rotterdam to the north, conceals a large concrete stairway leading to a parking garage. On the north side, it is connected to a ramp for pedestrian traffic that visually extends the bridge.
The Erasmus Bridge is a very good example of integrating lighting design into overall design of the bridge. Lighting itself makes a very important role in the design.
At night, the unusually subtle bridge is made to look even lighter thanks to a play of special lights that turns it into a mere silhouette.
Number 4. Akashi Kaikyo Bridge, Kobe, Japan.
The Akashi Kaikyo Bridge is the largest suspension bridge in the world. It is a miracle of Japanese construction and engineering, which made it possible to link the city of Kobe to Iwaya on Awaji Island, and which is also part of the Honshu Shikoku Highway. The idea to connect Awaji with Kobe emerged at the end of the 1950s in response to the tragedy which occurred in the Bay of Akashi in 1955. The collision of 2 ferries claimed 168 victims. However, it took more than 3 decades for the Japanese government to venture into such an ambitious and costly project.
When you see Akashi Kaikyo Bridge in Japan, it resembles to Golden Gate Bridge in the United States. It has a similar structure, it has also similar conditions, wind strokes, earthquakes.
It was not political or economic reasons that had been preventing the construction for so long, but the lack of technology that did not allow the construction of the bridge until the end of the 1980s. Less than 4 kilometers, or 2.24 miles wide, Akashi Bay is a place with extreme natural conditions. The sea depth here is around 100 meters, and the shore faces massive tidal streams at up to 4.5 meters per second. The whole area, busy with international shipping lines, is located in the typhoon zone. And to make it even worse, the bay is located on top of the boundary of 2 tectonic plates, an area with frequent earthquakes. These were the factors the Japanese engineers had to consider when designing the giant bridge. The construction of the Pearl Bridge, as the link between Kobe and Awaji Island was nicknamed, was started in 1988 by building massive bases for the embedding of the load-bearing cables. Simultaneously, construction of the foundations of the future 300-metre high bridge towers began on sea. They are based 60 metres below the sea surface and composed of gigantic steel cylinders of a whopping 80 metres or 262 feet in diameter. It took 7 years to complete the 2 towers and to stretch the load-bearing cables over the bridge deck. When it seemed that the construction was progressing successfully to its completion, a devastating earthquake struck.
Because of the extreme conditions in the region, this bridge was designed to absorb shocks and tremors caused by typhoons and earthquakes. In 1995, an earthquake destroyed many buildings in Kobe, but the nearly completed bridge survived.
The unfinished Pearl Bridge miraculously withstood. The opening ceremony was attended by more than 1,000 prominent guests, among which, of course, was His Imperial Highness Crown Prince Naruhito and his wife, Princess Masako. By the way, why was it nicknamed the Pearl Bridge? Apparently for its lighting, which thanks to 1,737 lights installed on all parts of its structure, can illuminate the bridge with any colour.
Number 3. Øresund Bridge, Denmark, Sweden.
Øresund Bridge is a part of a modern infrastructure that connects the Danish capital of Copenhagen with Malmö in Sweden. Altogether, it is over 16 kilometers or 10 miles long and consists of 4 parts: a 3.5 kilometer long underwater tunnel, an artificial, about 4 kilometers long island, a significantly smaller peninsula built up by the Danish shore, and finally, the bridge itself, named after the strait that it spans.
The gigantic proportions of this almost 8-kilometer long structure, the combination of road and rail traffic, and the fact that the bridge connects 2 states and 2 great cities, Copenhagen and Malmö, makes this construction one of the most interesting in the world.
Although the contract for its construction between Denmark and Sweden was signed in 1991, the idea to connect the 2 countries is considerably older. The first official record of it comes from the time around the year 1870. The technology of that time could not, of course, support such a challenging project. Search for an ideal route began only in 1990s. The most logical idea seemed to be construction of the bridge at the narrowest point of the Øresund Strait, that is, between the Danish Helsingborg and the Swedish Helsingborn, about 40 kilometers north of Copenhagen, where the strait is only 4 kilometers wide. Eventually, however, the current route won, though it was 4 times as long. The reason was that it had a much larger importance for both economy and transportation. The construction of the bridge, which was broadcast live through webcams, was launched in August 1995, and its last part was fitted 4 years later. From a structural point of view, the Øresund connector frame represents a combination of suspension and classical bridge, essentially a kind of marine estacade consisting of dozens of reinforced concrete columns. The length of the whole structure, which is the second longest bridge in the world, is a remarkable 7,845 meters. The first day of July of the year 2000, without doubt, became historic for both Denmark and Sweden. The Øresund Road and Rail Bridge was officially opened in the presence of Queen Margaret II of Denmark, King Carl XVI Gustaf of Sweden, Prime Ministers of the two countries and thousands of guests. The bridge is designed as a double deck, which means that there is a road on its surface and a rail track on the lower deck, where regular passenger trains run at a speed of 130 kilometers an hour.
The bridge is interesting in combination of road traffic on the upper deck and train traffic on the lower deck in truss steel bridge.
The first train set off from Malmö to Copenhagen on July the 2nd, 2000 at 6:09 a.m. First road vehicles crossed the bridge in the evening of the preceding day.
A combination of reinforced concrete decks with supporting trusses underneath was used in this construction.
Connection of the Öresund shores has not just fulfilled the old dream of the Danes and their Swedish neighbours to shorten the journey between Malmö and Copenhagen to just 35 minutes, but above all, it created a completely new region, a place where 3 million inhabitants who produce a quarter of Danish and Swedish national products.
Number 2. Gateshead Millennium Bridge, Newcastle upon Tyne, United Kingdom.
Gateshead Millennium Bridge is part of a project of renovation of the waterfront along the River Tyne in Gateshead in northern England, that together with Newcastle forms a conurbation. Gateshead Millennium Bridge is more like a functional work of art rather than a bridge in the classic sense. And because it reminds one of a huge eyelid that blinks whenever a ship approaches, the locals call it the Blinking Eye Bridge.
It's the first bridge which turns around its own axis to allow ships to go through, and which, when necessary, can raise the whole pedestrian and cycle deck.
In fact, however, it rotates on the huge joints embedded in the concrete struts on both banks of the river, thus creating a large enough space for the passing ships. Its unconventional technical solution makes this architectural masterpiece intended for pedestrian traffic and cyclists one of a kind. The bridge basically consists of two primary components: the bridge structure and the mechanism that elevates, or more precisely, rotates it a few degrees. The bridge is composed of a pair of steel parabolic arcs, one of which is a supporting arch which carries the deck curved in the direction of the river flow using the supporting rods. On the deck, there are two separate paths ensuring safe passage for pedestrians and cyclists. Another notable element is the elegantly shaped railing that evokes the railing of large ocean liners passing not far from there. The shores of the North Sea are not farther away than 20 kilometers.
The tilting function of Millennium Bridge is very simple. There are electrical engines that turn the bridge around its axis, and it tilts 40 degrees.
The second part of the structure is naturally the tilting mechanism. It consists of two large cylindrical pins. These not only rotate the bridge, but also hold it together. The tilting itself is performed by 6 hydraulic arms. The tilting mechanism of the bridge consists of a pair of parabolic steel arches, one of which forms a curved bridge deck, which is held by the second one using the system of suspension rods embedded into the giant joints. Tilting of the bridge, during which both arches act as counterweights, lasts less than 5 minutes. For this, impatient fellows waiting on the banks and at the helm of a boat should thank the sophisticated hydraulic system run by 8 powerful yet energy-saving electric motors. Another feature of this process is that every time the bridge tilts, it tidies itself up Earth's gravity causes all the litter to slide into special bins placed in the bridge deck. A competition for a design of a new bridge, attended by 6 designing studios, was held in 1998. The winning design was by the Wilkinson Eyre Architects Studio in London and civil engineers of Gifford and Partners. On November the 20th, 2000, the assembled giant bridge was delivered to the location. Thousands of curious spectators watched its installation performed using a giant floating crane, Hercules II, brought by towboats from the Netherlands, and they could also walk the bridge the very same day. However, the official opening of the bridge, which has also appeared on the £1 coin, was not held until May the 7th, 2002. Patience paid off richly to the constructors, as the bridge was personally visited by the British Queen Elizabeth II. In 2000, the 850-ton bridge, whose arch in the normal position of the bridge spans 50 metres high above the level of the River Tyne, was awarded the prestigious prize of the Royal Institute of British Architects.
Number 1. Millau Viaduct, Millau, France.
The Millau Viaduct is a masterpiece of contemporary engineering architecture and a record holder among the bridges of the world. Its length of 2,460 metres and masts, the tallest of which measures nearly 350 metres, make it the largest bridge structure of the world.
I think that French engineers need to push the engineering works a little bit further on. They are one of the best engineers in the world, and they succeeded in Millau Bridge.
When French engineers began building a new stretch of motorway, the A75, between the cities of Ferrand and Béziers, near the town of Millau, they encountered a problem in the form of a deep valley of the Tarn River. It could be bridged in several ways, so they thoroughly considered every alternative. In addition to the conventional concrete frame bridge, there were several types of truss and arch bridges among them. Finally, the project of a suspension bridge with 8 spans designed by Michel Villorgo was selected.
The collaboration between architects and engineers to apply new types of technology was very important during the whole construction of the bridge.
To build the bridge, Villorgo, one of the best bridge engineers of our time, decided to use a combination of concrete and steel, which, if properly maintained, can ensure a lifetime of at least 120 years. Villorgo went for steel and concrete not just due to their excellent properties or for economic reasons, but mainly for the structure of the bridge to look graceful and aesthetically pleasing. Therefore, he did not hesitate and invited the famous British architect Sir Norman Foster to cooperate. Thanks to Foster's artistic talent and Villorgo's engineering skills, the bridge, despite its size, does not appear bulky, but quite the contrary. It almost hovers over the valley of the Tarn River. The lightness and at the same time stability of the bridge is ensured by the huge concrete pillars resembling blades of grass. There are 7 of them, with the shortest being 78 metres tall. When we add the steel masts on which the supporting steel cables are fixed, the highest pylon reaches the impressive height of 343 metres. Each of the load-bearing reinforced concrete towers sits on 4 cylindrical bases. The lower part of the load-bearing tower is a hollow concrete parallelogram column. At a height of about 90 metres below the bridge deck, the pillars divide into 2 hollow shafts in a Y shape, which has its logical reasons. This solution increases the stiffness of the deck in its longitudinal direction while reducing its stress due to temperature changes. After they were erected by concreting 4-metre sections, the outer scaffolding was sliding automatically and the inner scaffolding was moved with a crane. Supporting truss steel structures were constructed in between the pylons. At the top of each of them, a specially designed sophisticated hydraulic lifter was installed, whose task was to lift the bridge deck up in regular intervals and move it a few inches toward the centre of the future bridge over the valley of the Tarn River. The construction of the bridge deck is a continuous steel girder supported by abutments of 7 intermediate pylons. The deck gradually advanced from both sides at a speed of about 10 metres per hour. After completion of this process, at the moment when both parts of the bridge deck precisely matched, welders connected the bridge and the steel masts bearing the supporting cables were placed on each pylon. You can't but agree that the Milal Viaduct perfectly merges with the surrounding landscape and belongs to the structures that, in addition to their main purpose, provide an attractive aesthetic look. Today's bridges represent works that would have never been brought to life without the sophisticated computers, cutting-edge building technology, and materials with incredible features. They are fascinating, breathtaking structures that seem to deny the laws of nature. Unlike many other spheres of architecture, it seems an indisputable fact that bridges are and will remain to be inherently linked with the life of people.